All right. I'm not going to make the mistake of having a mic that doesn't work. So I'm going to take a few seconds to make sure that that is true. Let's see. Gotta fix this. Okay. That looks about right. I'm just checking things. So, all right. Let's do this. Let's do a little pre-flight check. I'm going to open up the YouTube app and make sure that it's working, because there's nothing worse than recording stuff and it doesn't work. Pre-flight check. I'm going to open up the YouTube app and make sure that it's working, because there's nothing worse than recording stuff and it doesn't work. Pre-flight check. Because there's nothing worse than recording stuff and it doesn't work. Pre-flight check. Okay, I think we're good. That's good to know. So let's just make sure to post to twitter/x.com and let people know that we are doing this. We're doing this thing. Let's see. We're doing it. We're doing it live. Amazing. All right. So I think today we're going to read Service Router, which is hyperscale and minimal cost service mesh at Meta. I'll read the abstract. So basically, big companies, or many companies, but probably not everybody should, but some do, have these things called microservices, which are basically, you have some small functionality or you have some bounded functionality, and that is the thing that you want to write code for, and you want to deploy just that functionality. So it allows you to limit complexity. You can define a nice boundary around that code, and then it's running in the cloud, and it also makes it easier to scale. Like, imagine that you have two functions that are bundled in the same service that you're deploying or application that you're deploying, but one of them is actually way more popular than the other. It's easier to scale if you add the service that is in high demand independently of the other service. So that is a problem that microservices help to solve. However, they have recently come under fire because many people who probably shouldn't have microservices use them because they're technically interesting. There's some benefits. It's now easier than ever to deploy microservices. So Facebook/Meta almost certainly needs microservices or some formulation of microservices, because you wouldn't want just one application binary running that services all of Facebook. That wouldn't scale very well, and we know that Facebook is a non-trivial system to build, or has many non-trivial systems. So I'm going to talk about service. We're going to read the paper about service router, which is about a service mesh which lets services that are deployed independently talk to one another. So that's very cool. Let's download the paper and let's read it. It's also good to be back. It's on vacation, so I don't feel too bad about that OPSEC because, you know, it's fine. It's fine. Okay, so we're gonna load up Zotero, my favorite application, Zotero, and we're gonna read. All right, so let's start up some notes. Meta actually had a lot of papers at OSDI, which is pretty cool. Service router. And we're going to use the I'm still getting used to Obsidian, so there probably is a more efficient way to create the notes. Okay, so let's start the timer. 15 minutes. Let's go. Service router, hyperscale and minimal cost service mesh at Meta. It has authors from Meta and Carnegie Mellon. So hold on. Why is this not presenting? Hold on. Let's try this again. Oh, I see. That's why. We want this. There we go. Okay, perfect. So let's see if we can make this a bit bigger. And we want to read service router. What's happening here? Okay, interesting. Great. So, service router, we are now starting the 15-minute timer. And I'm going to actually just make sure, again, that it's all good. Okay, I've successfully checked that everything is good. I am now extremely paranoid that things are not good because I've made that mistake more than one time. Okay, so let's get started. Data center applications are often structured as many interconnected microservices. There are also other open source microservice service meshes. There is Linkerd. There is Istio. There are a few others. Istio. Other companies have examples of service meshes. So they're very cool. They're not just Meta. But they say that there are several differences. So it differs from publicly known service meshes. Okay, so it's hyperscale and tens of billions of requests per second. So there are probably a few other companies who have that. Google might be one of them, or LinkedIn, Microsoft maybe. Very large companies have this hyperscale. Maybe Apple must have some microservice thing. Although I'm not sure if I know about their tendency towards secrecy. I'm not sure if the services are allowed to talk to each other. Okay, so so this is interesting. So a common pattern is to have a sidecar, which is an application that is deployed alongside the main application, and the main application, whatever the microservice, then talks to the sidecar, which then does the routing. But in Meta's case, they actually have that type of functionality or proxy inside of the service executables, which does seem like it would have some pros and cons. For example, you could imagine that if the code for the proxy is directly inside of the service executable, but there's a problem with your proxy, then how are you going to fix it? You have to patch all of the service executables that have the library in them. So that seems like a con, but I'm curious if they've thought about that. Have they thought about it? Have they... Yeah. If they've thought about it, what have they thought? Did they decide that wasn't a con? Are there certain performance benefits to this approach? Because otherwise there are some obvious downsides. So that's just some interesting notes so far. So service router is embedded inside the application, which has some cons, potentially. They also talk about hyperscale, which is also true of other companies. It's not necessarily unique to Meta. Sorry. Differences between I may need to actually close my door. Okay. So hardware significantly reduces hardware costs. Interesting. Sharded services. Well, that's interesting. Because we also know about Shard Manager. Let's see if we know about Shard Manager, which is Meta's way of deploying sometimes stateful services and scaling them up based on traffic to specific regions or sub shards of servers. So it's interesting that they mention this. And they also talk about locality rings, which is pretty cool. Locality rings, which seems to minimize RPC latency and balance load. So I'm interested to learn more about that. Okay. Yes, they're talking about service meshes. We've already covered what service meshes are. Okay. They talk about the sidecar, which is what I mentioned previously. Okay. So features of service router are there are many features. Service discovery, load balancing, failover, authentication, encryption, observability, overload, which curious what they link to for observability. Okay, we'll come back to that. Overload protection, distributed request tracing, resource attribution, or for capacity management, and duplication of traffic for shadow testing. Due to space limitations. Okay, so they say, okay, well, we're not going to talk about most of those, and this seems to roughly map to the differences between service router and other proxies. But I like it's very straightforward about what they're not covering. Okay, they're saying that a centralized control plane is not ideal for a service mesh that runs at large scale. So they're talking about, so the example that they use is of a software-defined network. So that's basically you have some server that exists and it monitors routers and other networking equipment, and then based on signals that that controller receives, it then tells the routers to do stuff, aka the data plane. So route packets this way, so on and so forth. That is, I haven't read a paper about that yet, or I haven't written about it yet. However, there are papers that I like to read. There's one called Orion, which is a Google paper about the software-defined network. I also did write a paper, an article about a paper that built a software-defined network for balloons that were operating in remote regions. So that is on my blog. So anyways, they're saying that software-defined networking approach where you have the central control is not ideal. So that's interesting. Okay. So that's good. Okay, so we advocate for keeping the former in central control plane, but decentralizing the latter by transferring its function to L7 router. So they're saying there is still this function where you have some centralization. However, it's actually better to have the routing logic live in the edge, actually on the routers. And there are benefits to that. And then they compare a traditional sidecar-based approach to service router. Okay, figured this is to do. Cool. So they have a bunch of things that are actually made up of service router. So, wow, this is actually a pretty long introduction. But, okay. We'll get to that later. So, there are a few components of service router. We have the routing information base. We have the data distribution layer, which are RIB replicas. And then they have dedicated balancers, and they have sidecar proxies, and they have the library itself. Okay. So figure 2 shows service router scalable architecture. On the top, different controllers independently execute functions such as registering services and generating a per service cross-region routing table. Each controller independently updates the central routing information base and is not concerned with configuring or managing individual L7 routers. Okay. This also seems, another potential downside of this approach is that if you have the routers self-organizing, maybe there will be some emergent behavior that you did not anticipate. For example, how do you reset? Maybe it's solvable through an idea that I had. Like, how do you say, for example, all the libraries or sidecar proxies decide to start talking to a subset of servers because of some problem that you didn't anticipate? Now what do you do? Do you just restart the server? Do you push out some emergency fix? Decentralized control means that seems like emergency maneuvers could be a bit more difficult. So they're talking about this decentralized distribution, and they talk about how basically you send some information to this store, and then the controllers have all of this information that they aggregate in some way, and then they push it out to these replicas, which support a lot of read traffic. So this is like the write path, and this is the read path. A lot of reading. Okay. So, interesting. Okay, they actually talk about Istio. So hardware cost compared to Istio, which is one of the ones I mentioned. Okay, it would need the equivalent of 1 million AWS T4G small VMs to route 10 billion requests per second, which is kind of laughable if you think about it. I'm not really sure about this comparison, because you needed the compute power of the T4G small VMs, but I'm curious Well, you don't actually need 1 million of them because you have, I mean, is the sidecar on a per microservice basis, or is there one per machine? I actually don't know. But still, it just seems like this number is kind of, I don't know. It's laughably large. It's also 0.35 vCPU per. Well, actually, what is the okay? What is the cost of a T4G small EC2 info? I think has that right. So, because you can imagine, like, could Istio just work at immediate? It's ec2.info. It's been a long time since I've used EC2. Nope. EC2 pricing. I'm really showing how long it's been since I've used EC2. Can't find the calculator.aws. Is this good? Oh man, I don't create an estimate. Vantage. There was a EC2 instances. Anyways, I'm just curious how much this actually costs. So it says that a T4G small is 1 penny. 1 penny. Reserved pricing for 1 year standard upfront. So that's on demand reserved hourly price. Okay. So let's just think about this. Like, imagine that you did have, I guess, so let's do this. Hours in a year times 8,760 times we want T4G dot small. It is, the Linux reserved cost is 1 cent basically, and you want to have that times 1,750,000. Okay, let's make sure I enter the numbers correctly. So that's $160 million a year you'd spend on routing, which is a lot. That is a lot. But I'm wondering, there's no way that's the actual cost you pay, because Meta probably would get a discount on AWS. It just seems a bit, I don't really believe this number. I'm very skeptical. But maybe this is right. Maybe this is right. It's a lot. Okay. Okay, so service router eliminates the need for a proxy and its associated hardware costs, providing the service mesh function through a library called srlib. Okay. Yes. Okay. Great. So there are some pros and cons. Of linking. Some languages don't have support. Okay. Okay. I mean, this is pretty significant cost savings. It makes sense why they would invest in this. You know, how many? It's a lot of engineers. $160 million a year. Assuming that you're paying an engineer $1 million, which you're not, that's a lot of engineers. So I bet you that fewer than 160 engineers worked on this project probably. But I don't know. Sharded Services. So, okay, Sharded Services. So they also have some custom needs. Okay. So service router makes sharding support top priority and uses a single framework to support both sharding and replication. Okay. Okay, so this is another thing that I could see there being a lot of value in for cross-region routing, because Meta has many regions. They don't just have one region in US East. You know, they have a bunch of data centers. Figuring out how to route traffic across data centers is also difficult. Cool. This is very cool, actually. Locality rings, because you can imagine that there are some services that are not latency sensitive, and maybe they are on the path, maybe they're being used by batch jobs, so on and so forth. You could say, well, actually, we want to use lower tier resources. So that could be fine. And so if you're able to have that type of quality of service, maybe application quality of service, then that can be very helpful for cost savings. Okay, so what are the contributions? It's hyperscale, so it's working at very large scale. So yeah, I'm curious how many people are actually building service meshes now from scratch. They're maybe in developing markets. I would think that most of the Magma companies or FANG or whatever abbreviation you want to use, they probably have a service mesh already. So I wonder what the expectation is related to service meshes. Maybe it's about some of the differences, like the locality rings. Maybe that's not in other service meshes that are developed by other large companies at hyperscale. Okay. So hyperscale support a diversity of router types. Sharded services support, and then locality aware routing. A very thirsty dog in the other room. So now we're looking at the other parts of the paper. So we have comparison of service mesh architectures. We have service router design. We have the evaluation section, which looks very good. And I was actually just saying that nice standard systems paper where you have architecture, implementation, components, architecture and design components, implementation, and then evaluation. Very standard structure for systems papers. So load balancing, sharded services. So they have all of these things. Also limitations. That's really great because it's great to have it documentation on what the system cannot do. Later work and conclusion. So, okay. It's different in ways they talked about. It scales significantly. It scales significantly better. They talk about how it scales through this very read-heavy workload. They talk about decentralization or pushing some of the role, I guess, to the edge. So you actually have things embedded in the application that are making decisions, or closer to the application, not in the sidecar, that are making the decisions. Cost savings, locality rings, and sharded and replicated services. And then they talk about global capacity management and then degradation. So I've read both of these papers. I believe this is probably the Flux paper, which I read on a previous time. And then there's also the degradation, which talks about DEF CON, which is another paper that I read. So great. Let's look at the references. Scuba. I've also written about Scuba previously. Slicer. This is from Google. Delos. This is a very interesting paper by somebody who was active on Twitter, Mahesh Balakrishnan. I'm not sure if he's still active on Twitter, but has a very interesting blog as well. I've written about this one on my personal blog. Okay. They have the Google SRE book, Maglev. It's one I definitely Envoy. That's one that I forgot. Yes, global capacity management with Flux. I've written about that previously. Orion. This is the SDN that I mentioned. They talk about Finagle. I wonder actually if the link to the wow, they rebranded it to X Engineering. It's no longer Twitter Engineering. It's now X Engineering, even though the website is still blog.twitter.com. Do they actually have anything? No. The last thing they published was the recommendation algorithm. Amazing. So let's go back to what we were doing. So they talk about Finagle, which was a RPC system that was written in Scala. Is still used, I assume. They talk about some other load balancers. gRPC look-aside load balancer. Another meta paper. They talk about Cilium It's another one. Huh. I haven't seen this before. Looks fairly interesting. Related to Canopy. Tracing, performance tracing and analysis. Shard Manager. I've written about that previously. Oh, dynamic subsetting. This could be very interesting. Subsetting is when you choose which subset of a set of servers you're going to send traffic to. And then there are different fancy algorithms that you can run to decide that set and that subsetting. And then depending on how you do the subsetting, that can have different impact on tail latency, for example. So okay. It is very cool that they have these measurements for Istio. Definitely want to look at them. And they talk about Twine. I'm actually thinking about writing a series on welcome new people to the stream. I'm actually thinking about writing a series on different cluster managers, of which Twine is one. Can people hear me on the stream? Let's see if I can get any responses from chat about the quality of the audio. So, and then they talk about Borg. What else? Dissecting service mesh overloads. Oh, this is pretty cool. I wonder who published this actually. This was published by folks from ByteDance and IntentionNet. So that's very interesting. I'm curious how this fed into the meta work. Maybe they mention it. Okay, we are now ready to read the meat of the paper. So let's take a 5-minute break and then we'll read the rest of the paper. Okay, I've returned. And I will now check that my audio is good again. Is the audio still good? I will only make this mistake once, when I have recorded something and I was just muted for a while. And that was really bad because I I was just talking to myself. So now I'm extremely paranoid of... Yes, okay, audio is still good. Thank you, chat. Okay, so let's start reading the paper. Start a timer for about 45 minutes. That's about how long it takes. But, maybe it takes longer if we go on some tangents. So, okay, so let's... Comparison of service mesh architectures. So they talk about the design space in table 1. So the design space is determined by the answers to 2 key questions. Which component fetches and caches the routing metadata, and which component routes application RPC traffic? Okay. So in table 1, library, kernel, local, and remote mean that RPC routing or maintenance of routing metadata is performed by an embedded library. The kernel, a local proxy daemon on the RPC client machine, or remote proxy service outside the client machine. Okay. So this is actually pretty small. Let's see if I can zoom in. The complete solution space for service mesh. So which component manages and caches the mini routing information base, which I believe is like the routing metadata. So like, where do we route traffic to? And then which component forwards application RPC traffic? And they talk about let's zoom out. They actually talk about a few different approaches which are numbered, but where do the numbers go? Okay, so they've layered the numbers to, the numbers in the table correspond to sections here. Okay, so that's what we're gonna go with. So there are 2 questions. The 2 questions to solve are: where do you get and cache the routing information base, aka where you can route things to or route requests to, and then which component actually does the routing? Like, you have a microservice, and then the microservice wants to send some request to some other place where, and it says, I want to call foo service. Who actually decides which version of foo service to send it to, and figure out which machine that we're going to talk to for foo service functionality? Okay, so the first approach is srlib, solution 9 in table 1. So that is, okay, so it's a local. So this is something that is embedded in the application, and it runs on the actual computer. So that is this approach, I believe. It's a bit confusing how they laid this out, to be honest. So, okay, so they're just talking about the benefits. Okay, so they basically say, okay, we have a daemon that runs separately, and the reason that we run it separately is because it has very spiky traffic, and so that's actually very interesting. So they still do have some sidecar-like thing, but the functionality of the sidecar-like thing is very small. So that means that they've moved code between locations. So they have srlib, and there's actually two components, one of which has very spiky CPU usage, so it makes sense to separate. Okay, so, and they have this graph that shows the usage of this daemon that is actually doing this work that's very spiky. Yeah. Okay. So now they're talking about SR look-aside solution 13. Honestly, this table I am not a fan of. It's pretty confusing. Yeah, it's pretty confusing. So, or it's unnecessarily complex. So the setup shown in figure 4b and corresponding to solution 13 in table 1. So this is, you have a, okay, so figure 4b. Figure 4b, where's that? Okay, 4b, SR look-aside. Oh, this is very helpful to have this. This is what you want. So you have SR look-aside, where you still have this srlib embedded in the application code, and it talks to servers, and then it looks like if it doesn't have information, then I assume it goes to this SR look-aside service. Like it wants to talk to foo service, but it doesn't know where foo service is. Then this srlib talks to the SR look-aside service and says, hey, do you have it? If you don't have it, then I will get it. If the SR look-aside service doesn't have it, then I will go get it from the main source, which is the routing information base. Let's see if that's correct. Okay, so this is, okay, so yeah, so they're doing something similar to this, but they just move this code to an external place. They move, sorry, this code, which is running on every machine, to an external place. So that means that many machines can use the same functionality, looks like. So it actually looks like the SR look-aside service is very similar, it does something very similar to the rib daemon. Okay, so this is interesting. They have large fleets of small machines for power efficiency. Okay, so they don't even have this anymore. Okay. So this is 4C. So this is, you have a client on a machine who wants to talk to a server, and this is like This is like a traditional, or maybe not traditional, but this is like an existing approach called Istio, where you have a proxy that exists maybe on a per machine basis, and clients on the machine use that proxy. But it's saying even Meta's implementation is even better than Istio. Interesting. Does anybody know if services are written in Erlang? I'm pretty sure that must just be WhatsApp. I'm pretty sure WhatsApp is written in Erlang, not Elixir. WhatsApp Erlang, is that correct? But it says WhatsApp used to use Erlang. So let's see. SR look aside. They don't even use this anymore. Similar to Istio, but better. Mostly used for Erlang. Okay. Okay. So this is getting to some of the constraints of srlib. So if you want to embed some code inside of another service, then maybe they have to be written in the same language. We could also imagine there could be some foreign FFI interface. Like you could call, for example, if you wrote srlib in C++, could Erlang call C++? Maybe it wouldn't be high performance enough. I don't know. Hello. More people have joined the stream. Welcome. We are reading service router paper. I should probably link the actual paper for people who want to follow along at home, if I haven't done that already. So, great. So back to service router. So we've gotten through most of the approaches. Then there's this SR remote proxy, and you basically have a client on a machine who doesn't even have this routing, the local routing. It talks to a proxy, which then talks to the server. So this is common. A common approach for routing. So yeah, let's see. Okay, so now, yes, SR remote proxy is just traditional remote proxy. So they have different ways of running the infrastructure. That I think is the takeaway from this section. They have the capability to run different configurations. So, and this is actually better in some situations. It looks like if you have a better in some situations like cross-region. I'm looking at this figure to do figure 5. Or figure 5. Okay. So now we're going to talk about some of the comparisons. I find this to be needlessly complex. I'm honestly probably not going to read this section because they're talking about some things that are interesting, but it's just very complex to understand because of all the numbers and having to scroll back and forth between the table. So, finally for ease of access, we summarize in table 2 the comparison of the design alternatives. Okay, great. So hardware cost, srlib, direct RPC, good. Fast routing information. Save memory, maybe. Unchanged code, yes. Unchanged code, you have to change the code. That's pretty bad. That seems like a pretty big con, actually. Shared connection, also bad. Then sidecar proxy. The thing is, the unchanged code is such a valuable pro. I don't know. I'm not sure how that's canceled out yet. And they talk about the different attributes. Okay, so yeah, I'm actually just really baffled by this. I guess I'm trying to think if there are other examples of this type of pattern where you're embedding the library and there isn't anything in between. I think that something might exist. I think something might exist, but yeah, I think something might exist. So okay, they talk about some design of service router now. So they talk about to do figure 4, which shows and now they're going to talk about some of the components. Okay, we're already somewhat familiar with these components because they've talked about them previously, but they have the routing information base. I guess these are the higher level components of service router. It uses Paxos. Paxos is a distributed consensus algorithm. Uses Paxos. Okay. Then you have the GRS, which is the Global Registry Service. Service and shard discovery. It shows you some examples of services in GRS. Okay, so you have, for an unsharded service, you have where it is, which IP address and which port you can reach it on. And then for a sharded service, you have which shards the service has at a specific IP and port. So that's pretty neat. But otherwise, this is something that you would have in a service discovery system. Like there's another one called Console, or you could use Zookeeper, or you could use etcd. There are all these service discovery mechanisms where you put, it's a key value pair essentially, or there's some storage mechanism. The actual way of storing things it depends on the system, but you can store this type of information essentially, and it's replicated, and you don't have to worry about data loss, and everything is awesome and consistent. Okay, they're going to talk about the sharded services. So configuration management system. So customize the routing policy. And there's some configuration via code that is committed. Then the cross-region, XRS, cross-region routing. Okay, so essentially if you want to send traffic across a region, srlib might not do that correctly because maybe it only has information about the region that it's in. So this helps with that, with making optimal decisions. And they have some, okay, cool. So we're going to learn a bit more about how the service router works now. And in particular, we're going to learn a bit more about cross-region routing. They also mention this thing called LMS, Latency Monitoring Service, which periodically aggregates and commits configuration updates related to cross-region latency. So there's some automation around minimizing cross-region latency. Okay, so let's talk about service discovery. Yeah. So we have this rib daemon and we have the mini rib. Okay, this is important. Mini rib is empty when it starts, but then when our srlib wants to send an RPC request to a particular service, such as service X, it requests services X routing metadata from the rib daemon, and then the daemon goes and fetches it from a rib replica. And the rib daemon takes some steps to make sure that it doesn't lose the information. Mini rib daemon, local cache basically is what the mini rib is, and then the rib daemon takes steps to store the rib, like persisting to disk. Okay. Then the srlib also caches stuff. Okay, so then there's this waterfall thing when a cluster manager, I think in this case, it's called Twine. Twine informs the GRS here about some change. Then that gets pushed down to the RIB replicas, which, because RIB daemon is subscribed to the RIB replicas, then the RIB daemon gets it, and then eventually the RIB daemon pushes it to srlib. Okay. Okay. So they also talk about, like in the happy case, the cluster manager will remove entries up for a service before shutting it down. In bad situations, the cluster manager still Okay, so now we're going to learn about sharded services. Okay. Okay. There's a lot of content in this paper, so I think we're going to accelerate probably. So, support for sharded services. So clients can ask for keys and primary/secondary of the service, and SR figures it out. That's interesting. I'm curious what applications do for sharded services with Istio or something else. Okay, they talk about consistent hashing. Yeah, so they're basically saying we use Shard Manager. So there are other approaches. Basically, there are other approaches for sharding, but they don't really experience use at Meta. They talk about consistent hashing, and they also talk about look-aside. consistent hashing, yeah, one of the reasons that I can imagine that they don't use it is because they say that it's not as flexible with respect to dynamic migration of shards. And then they also talk about how there's this local site approach, which turned out to be fairly complex. So anyways, there are other approaches. Okay, load balancing. So they have they have pick2, but they also have other approaches. Okay. Okay. They have different load balancing approaches. Okay. Okay, so it doesn't take locality into account. Okay. Okay, so basically look for two servers that are in the closest ring. Okay. So they have some solution for there's some cross-region routing table that they're talking about. Seems very interesting. Let's come back to it. I like the detail. It's very cool. Okay, design alternatives. Yeah, again, gonna come back to it. It seems very interesting though. Okay. Okay, so there's some random subsetting or subsetting approach. That's cool. That's also very cool. So I think this is interesting because they're talking about using a different hashing mechanism to choose servers to send requests to. And they explicitly talk about using this approach called a rendezvous hashing. Where is it linked? A name-based mapping scheme for rendezvous. I have not read this paper. What else is the other one that they referenced? Number 9. Rendezvous hashing explained. Oh, amazing. Okay, I'm definitely going to read this one. Rendezvous hashing explained. Very cool. I'm excited to read this. I like the numbers. I like the numbers in it. Or I like the graphics rather. Welcome to the stream. I saw new people joined. Hopefully my audio works. Please let me know if I'm quiet. You wouldn't know. You wouldn't know that I'm asking you if I'm quiet. How's the audio? I just have to ask this on a recurring basis now because I've been traumatized by not having the audio for a long time and people wondering where I was. So hopefully somebody will respond. Hopefully chat will respond. So, okay, where were we? Let's go back to the rendezvous hashing. We're almost done with the meat of the paper, and then it's going to be the evaluation. So I will circle back to rendezvous hashing and inconsistent hashing because I realize we're almost out of time. So they're talking about pick 2, which is this routing, or just a random pick 2 servers. So this is the third approach where they also route based on load. Okay, that's cool. I like how they talk about the different choices and the reasoning behind these somewhat smaller optimizations. I would be interested in hearing, hopefully in the evaluation, they talk about some of these options for you know, hopefully they talk about some of the options for routing, service routing, and how they impact the scalability of the service. But we'll see in the next section. Okay. So that was a loud door close. Just based on the weather. So, okay, one thing I want to go back to is, are they using all of these at once, or is it a combination of these techniques? complement. So it makes it sound like they are using them all at once, which is interesting. So the 3 techniques, there is think about regional locality. How far away are the servers that you are picking randomly from? There's also reusing the same connection has some overhead, so make sure to reuse the same connection. And then there is the adaptive approach, which is to take load into account. So now we get to discuss the evaluation. We're on the tail stretch of this paper. So I think we'll just go through. Maybe we won't get to the other components. For example, maybe we won't get to the I don't know. We'll see how much we get through. I'd like to at least get through the evaluation. Okay, so they're going to answer 4 main questions. Oop, not that. That's YouTube. Share link. No, we want this. Okay, so does it scale? Well, I think we know the answer to this technically because the system has been used in production since 2012. So my guess is that it does scale. That would be my guess. No responses on how the audio is, so I'm just going to be hopeful that it's good. If the audio is good, please chime in the chat and tell me that you can hear me. So to understand the scale of individual services, we plot the number of servers used by services in figure 8. A small fraction of services are very large, while most are very small. Okay. 2% of services each use more than 2,000 servers. Largest service uses 90,000 servers. Is that servers or services? It must be servers, like actual machines. Okay. I'm curious what the hyperscale services are. Okay. Okay, they talk about, oh, I really like this. So many servers use few services. Many services use few servers. Servers, some use a lot, and then there's a wide distribution in requests per second. And then I really like this. They start talking about the potential bottlenecks. That's novel. Wow, we're trending up. Welcome to the stream. Hopefully my audio works. How's the audio? I just keep asking this. I keep polling for how the audio is. hoping that it's good. Nobody said anything, so hopefully it's good. Okay, cool. So there's this thing called the rib, which contains information about the routing that is possible, and it's pretty large. Okay, so they talk about using Zookeeper. Okay. So they can shard it further if needed. Okay, amazing. Thank you. The audio is good. The audio remains good. Okay. So distribution of rib is fast, far from reaching any scaling bottleneck. Okay. Okay, due to the propagation of delayed service discovery information, any system that does service discovery and routing will have some stale routing information. Okay. What's this previous work? Shard Manager. I've read that. Shard Manager is also described on my blog, michaellearn.com. If you search Shard Manager there's something about it. Okay. So they're not worried about the other things scaling because they all have a rib as the bottleneck. Okay. Oh, okay. Cool. So then they talk about the routing configuration changes are broken down by a few things, and then they talk about what those are. So they talk about sounds like the top types of changes are processing timeout. So that would mean that the server RPC server RPCs are timing out. Then we have locality rings, so like which services are near one another. Then we have traffic shedding, which is, if we need to shed traffic for a client ID. That's a new idea that they're introducing here, but I assume that specific services have client IDs that they use, and the traffic for those can be load shed. And then they have shadow traffic, so that would be like if you're doing a quote-unquote dark launch of a service and you want to send traffic to the new service, but it doesn't actually do anything, you just want to test. So that's shadow traffic. So the changes to the shadow traffic. And also, they're talking about locality ring being important because that's a novel feature. Okay, so now they're going to talk about hardware cost, which is supposedly one of the big benefits of SRlib. Okay, and they talk about the different RPC setups. There's SRlib, which is embedded. Then you have SR proxy, which is like Istio. Then you have Thrift, which is just a basic RPC thing. No load balancing, really. Basic RPC mechanism. No routing, really. Okay. So, okay. Yeah, so Thrift is like gRPC. It's you can define an API, and it's, I'm not sure if Thrift is actually deprecated. Thrift, not Thrift stores. Thrift RPC. Oh, it's an Apache project now. Anyways, thrift.apache.org is the thing. Okay. Okay. So they're just saying everything is standard across, or for the most part, it's standard across the different setups. You know, requests and responses are the same. And then they talk about what the overhead actually is. Okay, so they have some setup that minimizes the other things that contribute to RPC processing, which makes sense. So they're saying that instructions per request. So okay, great. So they're just basically saying, wow, you have Thrift, which is the most basic. srlib seems like it actually has slightly better or the same as Thrift. And then you have srproxy, which is obviously way worse. And then you talk about the instructions per the request. And you're basically wasting a bunch of instructions at the proxy side. So that makes sense. And I think that's actually very similar to what their argument is with not using Istio, because Istio has this proxy component. So yeah. So basically RPC latency approximately similar for Thrift and srlib, and srproxy is a lot worse, relatively. And then you show the figure 10. Okay. So if they would need hundreds of thousands of more machines if they used srproxy, which is the thing that they're saying about using something like Istio, which there are all these wasted instructions, wasted computation on the proxy, the sidecar. Okay. Oh, and okay, they also break down my payload. Okay, cool. They also mentioned something like zero copy data forwarding. Zero copy is a big thing between the kernel and the end user space. It means you don't have to copy memory. So if you can do that, amazing. So that might be actually where they're talking about the small difference is that small improvement of srlib over thrift is just based on they think it's a little bit of error. Okay. So they're going to talk about when to use SR proxy. Case study. Okay. This is very cool. I really like these case studies. So there's some case studies. There's some case studies where they're able to say, trade off this latency for this amount of cost. That's very cool. Very cool. This distributed key value store. So connection reuse is big. Connection reuse is big. Amazing. We have so many people on the stream right now. Welcome. So now we're going to talk about load balancing. I think once we finish the evaluation, then we'll be done. Because the limitations, you can read the paper review later. So load balancing. So SR performs load balancing both within a region and across regions. So okay. Okay, so what are we looking at here? So load balancing within a region for unsharded and sharded services. Top group shows the normalized average load, and bottom two groups show the load's coefficient of variation across servers. So I'm a bit confused because I'm colorblind and I really struggle with this graph. So I'm not really going to be good at this one. So okay. So they're basically saying that the coefficient of variation is low. The load is low. So that is, or the coefficient in variation of load is good. It's good that that's low because it's low, that means that load balancing is happening well. So so there's like very similar load. This is same region. Very similar load for unsharded services, which is good. And for sharded services, they basically say that the can differ significantly, but it's not because of SR. It's not because of the routing. It's because there's just some inherent differences. There are inherent differences in load because of when you have a sharded service, some shards will be getting more traffic, and there really is anything you can do besides, well, Shard Manager is Shard Manager, which is Meta's system for managing information or services that are in shards, that actually should be handling this. So it's not a problem with the load, but I'm not sure how I feel about that. It seems like if the system was working perfectly, then Shard Manager would work well, and also the load balancing would work well. So I'm going to read it in a bit more depth. So yeah, so they do talk about it, but so it's not, the load imbalance is not so bad that Shard Manager tries to fix it. So that's what they're saying. So it's a Shard Manager problem. So now we have cross-region. Okay. So most services use the default locality ring, which is basically try to talk to services that are closer with some caveats. So Okay. Cool. So they talk about okay, XRS shapes the services traffic across several regions to prevent overload. Where's this? Oh, spillover. Okay. Nice, nice. Learning from production. Love that. So they're talking about some system that has large, this is really cool. I think this is really cool. Overload. I'm aware of this idea, but I am not sure. I have not seen people outside of companies I worked in implement it. During a spillover event, traffic shifted to different rings, basically. Very cool. Learning from production. Okay, very cool. Very cool. Little impact to users. Okay. So this is answering the fourth question. Are sharded services important, and can service router effectively support both sharded and unsharded services? That's what we're looking at here. The fourth question, the last question in the evaluation, and then that will be it for tonight. Okay, so figure 14a shows the aggregate request per second for all sharded services is 212% of the aggregate request per second for all unsharded services. Okay, that seems good. That seems to indicate that it's important to support sharded services, and that service router is able to do so. Okay, so they talk about two things. They talk about how much traffic actually goes to sharded services. It's a lot. And then what is the overhead of sharded services? And it says that actually the sharding thing means that there are many configuration changes to where traffic is routed. Okay. So it says, overall, the traffic of sharded services overwhelmingly dominates both the data plane and the control plane of a service mesh. So the data plane is where does the actual traffic go to sharded services? Or where does the actual traffic go? Is it going to sharded services? And then the control plane is all the changes to services and where they're routing their traffic. Many of those are many of the changes are related to shards and sharded services. So the answer is yes, this is important. So yeah. Okay. So I'm really tempted to do the limitations as well, because why not? We could just keep going. We can keep going, and then I think it's time to log off. So limitations, srlib, and our solutions. So dynamic policy updates. Yep. So they're basically saying, we know that compiling things into applications isn't the best. But there are meta solutions for solving configuration propagation. Yep, okay, amazing. This is the main point that I noted at the beginning of the paper, that they're trading off this, because they're embedding srlib in the actual application code. That means that if they want to make changes to srlib, they need to redeploy the application code. Oh, actually, No. This is not what I'm saying. This is not what I said earlier. This is that you need to change the call code to use srlib. Okay. Yeah. Okay. So basically, it's not a big deal. So that's actually a separate problem. I think we're gonna get to the problem that I noted. So source code, you have to modify the call sites to use library, and then library code development. Yes, this is what I noted, I think. Okay. Okay. It seems non-trivial. This seems extremely non-trivial. Because how do you know that this, how do you know that deploying srlib in your application is not going to cause some problem for some applications that are using it, and maybe it introduces more tail latency? This may be continued on the next episode of Micah Reed's papers when we read the conveyor paper, but I'm curious how, for example, the canary changes. This seems unsafe. Move fast and break things? Move fast to break things? I'm not sure. Yes, exactly. This is exactly what I'm getting at. But I'm curious what they say. Okay. So every major code change is gated by a configuration parameter. Yeah. This seems yeah, it's possible. But what if the configuration change and actually canarying it? I guess theoretically you have really good canary analysis that you're capable of doing, but what if you don't detect the problem until it's been out there in the wild for a long time? And then suddenly you have this feature deployed to your whole fleet. That seems pretty dangerous. More dangerous than having a sidecar. But maybe it is worth the risk, considering how much money you're saving. So, gating. I would actually have loved to read this design doc and hear what people thought. But that also seems dangerous. Okay, so okay, so here it is. This is actually the main point that I made. Okay, so they're saying it's worth it, which I think is such a cool decision to make, because they're saying there's this risk, we acknowledge the risk, and we're still going to make that decision because it saves so much money, which is so cool, because I think to even be in the position to make that decision, you must have done a lot of analysis. So anyways, that's it for today. We read Service Router, Hyperscale, and Minimal Cost Service Mesh at Meta. And thank you for joining. Until next time, I'll also publish the notes on the website. See you then.